In the last video, we discussed how any infinite set that could be listed out is the same size as the natural numbers. It seems counterintuitive, but there are just as many natural numbers as there are prime numbers, as there are integers, as there are rational numbers. At this point, it may seem like all of the infinities are the same size, but actually, some infinities are bigger than other infinities. Let's say you have an infinitely long row of Pokeballs. Inside each Pokeball can be either Charmander, Squirtle, or Bulbasaur. How many different rows can we have? For example, we might have a row of nothing but Charmanders. We might have Charmander, Squirtle, and Bulbasaur repeated forever. We might have a totally random and unpredictable row. There's an infinite amount of possibilities, but just how large is that infinity? Well, it must be at least as big as the size of the natural numbers. To see this, we can create a surjection from the Pokemon to the naturals, or a mapping such that every number is mapped onto. To do this, let's say that the row of all Charmanders goes to 0, one Squirtle in all Charmanders goes to 1, two Squirtles in all Charmanders goes to 2, and so on. The mapping itself is fairly straightforward, and shows that the amount of Pokemon rows must be at least as big as the amount of naturals. Now the question is if the reverse is true. The number of Pokemon rows is actually way more than the size of the natural numbers. To get an intuition as to why this is, let's try mapping from the naturals to the rows by listing out all of the possible rows. Maybe we start with the row of all Charmanders, but what comes next? Perhaps we have Squirtle followed by all Charmanders, but then why not Charmander, Squirtle, then all Charmanders? But then why not two Charmanders, Squirtle, then all Charmanders? It's easy to get stuck trying to figure out what should come next. This isn't a proof that these rows are unlistable, but illustrates that there's something special about this set. We're going to prove that the amount of rows of Pokemon is uncountable using a technique called proof by contradiction. Let's say you want to prove something like pigs can't fly. You start by assuming the opposite, pigs can fly. You then proceed to make logical deductions, and eventually you arrive at a contradictory conclusion, such as 1 equals 2. In order to arrive at an illogical conclusion like this, the initial assumption must be false. Therefore, pigs can't fly. Let's try it out for real. Assume for the sake of contradiction that there are just as many rows of Pokemon as there are natural numbers. We know from the last video that this means that there's a bijection between the two, or more simply, that we can list out all of the rows of Pokemon. Let's use this list as an example. As a side note, we're only using this specific list for illustrative purposes. We don't need this specific list for the proof to work, we just need there to be a list. Take the first Pokemon from the first row, the second Pokemon from the second row, the third Pokemon from the third row, and so on, and string them all together to create a new row of Pokemon. Now, take each Pokemon in the new row and change Charmander to Squirtle, Squirtle to Bulbasaur, and Bulbasaur to Charmander. This fully transformed row is just another row of Pokemon, so it must appear on this list somewhere. Now, the question is, where does this row appear? Is it the first row? Well, it can't be, since the first Pokemon from both rows were designed to be different from each other. The second Pokemon from the second row must also be different from the second Pokemon in our new row, so our new row can't be the second row. In fact, if you take any arbitrary row I, we know that our constructed row can't be the same since the ith Pokemon from both lists must be different from each other. Since this row can't be any of the rows on the list, it can't be on the list. But we initially assumed that this was a complete list of all of the possible rows. This means that the row is both on and not on the list, which is an obvious contradiction. How can we reconcile the contradiction here? Well, because everything we did in the proof was mathematically valid, there must be something wrong with our starting assumption. There are just as many rows of Pokemon as there are natural numbers. Therefore, there has to be more rows than natural numbers. Even an infinite list of the rows isn't big enough to contain all of the rows. If you had a bag containing all of the rows and kept pulling them out one at a time forever, there will always be rows that you can never grab because there are so many of them. At this point, you might be thinking, who cares about Pokemon? Well, actually, This argument is essentially the same to prove that there are way more numbers between 0 and 1 than there are natural numbers. Just replace the Pokemon with numbers, add a decimal point in front, and we can use proof by contradiction with diagonalization to create a number between 0 and 1 that should be on our list of numbers, but can't possibly be there. This establishes two different sizes of infinity, the amount of natural numbers and the amount of numbers between 0 and 1. Is there a size of infinity that lies between the two? Georg Cantor, the man who developed the diagonalization method, set out to prove that there wasn't. This problem is known as the Continuum Hypothesis, but unfortunately, Cantor died before he could find a proof. That's because the Continuum Hypothesis is actually an unsolvable problem. Note that this is very different from an unsolved problem. An unsolved problem is a problem that we don't yet know the answer to, which mathematicians are actively trying to solve. We know the answer to an unsolvable problem, and the answer is that there is no answer. Paul Cohen proved that we can't prove the Continuum Hypothesis true or false. This sounds like a really strange answer, but is a larger topic for a future video. So we have countable and uncountable infinity, and we can't say if there's anything in between. But is there something even bigger? There is. The power set of any set is larger than the original, and we can repeatedly take power sets to make a larger and larger infinity. If you want to learn more about power sets, check out the description below. For this video, what we care about most is the difference between countable and uncountable infinity. The mechanics of diagonalization specifically are going to be important for us in future videos. Now that we understand this topic,
to infinity and beyond!